Hey guys, uh, welcome to tutorial 7. Hopefully the stream's running fine. I just realized that I had set it to private like a minute ago, so I changed that. So hopefully people can hear me, can see the stream. Can you guys hear me fine? Just anything in the chat. If anybody can hear me, okay, cool. All right, so we have a question from Lacey about going over an A4 question, and we can definitely do that. We have to get through a little bit of content, but I can definitely get to that at the end. And luckily, this content isn't too bad, so let's quickly go over it. So, the plan for today is to do a little bit of exception stuff and base conversion. So this is what we are going to be doing. Stuff like that. Yeah. So we're going to do a few functions here. And so let's open up a cell. And I'm going to have you guys take a look at the functions, and some observations can be made about them. So let's code a very simple average function that takes in some list and produces the average, right? So how would you do that? Well, you need the sum of the list over the length of the list. So traditionally in Python, what you could just do is something like this. And you'd return that, right? But instead of doing this, let's do it the way you do it via an actual program without using these built-in functions that Python gives you. If you're doing this in any other language, you'd have to actually calculate the sum yourself. So how would you do that? You could say like my sum is equal to 0, and then you could say for elements in list, my sum plus equals element. And then once you have the sum like that, you could just simply do, we could say average is equal to my sum divided by the length of the list, right? And then you could return average. And you could put that on one line or whatever, but this is kind of the idea. So immediately, since you guys know that this is about, oh, can I zoom in? Sorry, didn't see that. I can zoom in. Hopefully that's a little bit better. Let me know. Yeah, so this is our average function. And since we're looking at error handling, maybe you guys can think of something that could go wrong with this function, specifically regarding the input. And so we can see that this function isn't fully safe, right? Because there are some inputs that will break it. And by break it, I simply mean raise an error, right? So let's see how we could do that. If we try to run this average function with an empty list, for example, look at what happens. Python raises a 0 division error, which is an error that happens when you divide by 0. So Python realized that it was dividing by 0 here because the length of the list is 0 with an empty list, which is a division by 0. So as soon as it saw that it's dividing by 0, it raises a 0 division error and crashes your program for you. Not only this, but if we called average with a list containing types that couldn't be summed, right? This line right here is another source of possible trouble. We could crash the program in this line if elements was not an integer, right? So if we had like, let's say like 2, 5, and then a string, for example, or you'd see that here, Python raises a type error. Why? Because it's trying to add a string to an integer, right? My sum is an integer because we defined it up here, and you're trying to add a string when element takes the place of, when the string Basil takes the place of elements, this is going to be a string, and this is where it's going to crash. So we can already see a couple different different ways that this might crash, right? So let's just do this, clear our output. And now what we're going to do is, you can see we've coded our naive average function. Let's try and code a safer version of this function that takes into account these risks and uses error handling, which you guys learned about in class, hopefully, to mitigate those risks and to fix them, in a sense, right? So it's very simple. We're just going to do average safe again, and pretty much the same idea is going to happen here, with one exception. And that is that we're going to basically enclose our whole function in a try block. So we're going to use a concept called try except. Just like this, I'm going to say we're making the average function safe by using try except blocks. And the way you can do that is just put a try up here and tab this in so that all of this code is now part of the try block. And for every try, you obviously need an except. And what's going to happen here is basically Python tries to execute, right? That's why this keyword is try. It tries to execute this code. And with this except, we're basically saying that if at any point during this try block we run into an error, then we're going to jump outside of the try block and to the except block. And we're going to basically run this instead. So instead of crashing the program, right, instead of it returning an error and crashing your program like this with a whole error trace, what you can do instead is use this try except. And so you can see that if we now take, for example, let's say this empty list error, this erroneous test case, and we try and print it. Hold on. So this could be a thing with the return value. So let me try and adjust that, because we should be seeing this error occurred instead of the actual error being raised. But we're still seeing the error being raised. So why is that? My sum. If we said zero division error to specify the actual error that we're talking about, oh, we're calling average. Oops, sorry guys. That's a dumb little mistake. This is average safe. This is a totally different function. So we were still calling our broken function up here, right? Let's save this. So yeah, you can see here if we do this, ooh, AVG. Yeah, let's put this return back here so that we're not referencing something that potentially was not defined. And now if we run this, you can see that it actually works. Our error got caught. So even though we're dividing by 0 up here, instead of throwing a zero division error, it does raise a zero division error, but it gets caught, like that error gets caught in this except block. And so we're safe. And the reason we have a none here is because since this line of code never ran, AVG never got assigned a value. So AVG is still technically in programming, it's called like a null pointer because it's basically a variable that's pointing to a spot in memory, but it hasn't been assigned anything yet. And since it hasn't been assigned a value, its value is just none for now. And so it gets returned as none, right? So that's fine, and that's kind of expected because we should be returning not a number if the average can't be taken, right? And you'll see here, what if we try and comment this test case out and instead use our different erroneous test case? And remember to actually update the name of the function. You'll see that we get the same thing. And so this is great. We've learned to mitigate errors via error handling and to actually catch them before they crash our program, which is a very important tool in programming. Now we can actually go a step further with this, and as you would have seen earlier, you can actually specify exactly which error you want to catch. And so we can say something like zero division error here, and say a customized message, or we can run some customized code for when we get a zero division error while trying to do this. Something like that, right? And then we can have another different except block for our type error, which is when an incompatible type tries to get added to an integer. Something like that. And you can see now we get our custom error message because what happened here? So everything went fine, right? Up to here, we tried adding a string to an integer, and so Python raised the type error on this line. So what ended up happening? It broke out of the try block, came up here to the first except, and it checked. It starts going through every except, right, to see which one it matches. Right now, it raised a type error. So it checks here. Is this an except block for a type error? No. So it skips it and moves to the next one. Is this an except block for a type error? Yes. And that's what we have. So let's execute this code inside it. And that's exactly what happens. Cool. So what should we do next? Oh, also, you can still also have that general except, just like we had earlier, and you can combine it with specifying certain errors. So you can say here, an error was raised, for example, that wasn't type error nor this whole thing. Cool. So I don't even know how we can break this code with a different error besides these two. So maybe this would actually never even have a possibility of running, but you guys get the idea, right? If we added some more functionality down here, whatever that enabled an error to be raised that wasn't these two, then if that error was raised, this part of the block would be ran, this except block. Cool. So here we are catching specific errors. And here we're catching all remaining, I guess, other errors that weren't previously specified in an except block. Okay, cool. And that's pretty much average safe. So you can see that we've made our average function that was pretty naive up here significantly safer against bad inputs. So now bad inputs can't really hurt it that much. And that's pretty much it. So let's do one more. And this one's going to be called, I think, up here, 1 to 10. So what's this function going to do? It's just going to take in an input. And really simply, it's going to do something like this. It's going to say, if x is less than 1, or I guess we should say, if x is greater or equal to 1, and x is less than or equal to 10, then we'll say print, your number is within the acceptable range. You can say else. Something like that, right? And so what I want to show you guys is that there's kind of like two methods of doing this, is that you can use try except blocks to catch the errors, or you can kind of just avoid the errors yourself. And these are two different methods, and they're useful in different scenarios. And the way you know which one to use is kind of, if you can already spot the exact reason why an error might be raised, and you know for a fact that it's only confined to that specific reason, then instead of letting the program raise the error, you can just avoid raising the error altogether by using conditional branching to just avoid it ever, right? So just like that, right? Like if somehow numbers that were outside of this range were unsafe for our program, we could just split them off into different branches, right? Or simply just not accept anything in this branch and then do all of our math here. Similarly, if you had like a def divide by n, so like let's say we're dividing 10 by n, right? And we want to say print 10 divided by n, right? That's great. But what if 10 is 0, right? If we do something like this, divide 10 by n, we pass in a 0, we get a 0 division error. So we can avoid this by saying if n is not equal to 0. You see what I mean? And so now nothing happens. So these are kind of the two different approaches to error handling. And hopefully you guys see the differences and understand the explanations on why they're different and why they're it might be more preferable to use one in different scenarios over the other. Cool. So that's actually all we're going to be doing for error handling. We're going to be doing a little bit of base conversion. And then we're going to take up the questions that anybody had, including going over a bonus question from A4 recursively. Okay, so let's do this base conversion stuff. So we have our first function, which is we're going to be going from decimal to base 32. Now, as you guys might know, there are already functions for going from certain bases to others, like the hex function, right? Which is built into Python. There's no function for going to base 32, at least not built into Python directly. I'm sure you can find some libraries for it. But the idea is that we're going to try and code our own base converter for going from decimal to base 32, and then we're also going to go from base 32 back to decimal. So we're going to see how we can code the conversion both ways. And knowing how to code these conversion functions is actually pretty useful, and you guys might find it pop up on your future tests, who knows. So the first thing we want to do is define our base's alphabet. So we're just going to be doing something like this, right? Whoop, and then A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Now let's actually count this out. So we have 10 here. Let me just finish this. Q, R, S, T, U, V, W, X, Y, Z. So we need 32. So that's 10 right there. 5, 20 right here. Oops. 5, and another 5 right here, and 2. So we're going to cut off at V. Basically, this alphabet gives us 32 different possible symbols to represent our different multiples of that power, right? Just like how in hexadecimal, you have 16 different symbols to represent what you can store in hexadecimal, right? 0 to 9, and then A through F. And just like how in decimal, you have 10 different digits to represent your different multiples, right? And so now we have the alphabet. And we want to convert from decimal, so this is going to be a number, and we want to convert it to base 32, which is going to be a string composed of these different alphabet characters, right? Now, how would we do that? There are a bunch of different ways to do it, and actually, like some of the other TAs, when they ran their tutorials, they did it in completely different ways, but I'm going to code mine here. I'm going to code this function the way I would do it. And this is the way that I kind of always thought of these conversions, especially like base 2. And this is how I do it, right? Let's first just give ourselves a string to store our result, which is what we're going to be returning at some point, right? But the way I do this is first I find the largest power of 32 that will fit in our number. And maybe you can see where we're going to go with that, right? We're going to take the largest power of 32 that fits in our number, and then we're going to just keep going down the power list and seeing what fits in iteratively. So let's call this current power. And there's a few there's a few different ways to do this. You can do it iteratively. You can actually write a function to find this largest power. Or what we're going to be doing, just to save some time, is we're going to be using the log function. So we're going to be doing math.log of x with a base of 32. So log takes in the number that you're logging and the base that you're logging it under. So we're using a base of 32, so we're going to pass in base 32 here. And this is going to be the log. Now, as you know, we want to take the largest power. And when I say this, I mean the largest whole number power, right? And for the largest whole number power, if, let's say, for example, our number was 33, this log would be right over 1, right? It would be right over 1. But we want to get 1. So what we're going to do is we're just going to chop off the decimal of that log. So now this works. And you'll see that if we call this function on something like 33, now we get 1, which is exactly what we want to do. Whereas if we left this int out, we get something right over 1 because it's right over 33, right? And I'm sure you guys know how your logs work. Yeah, so let's put that int back on there. And what we're going to do once we have that power is we're just going to start decrementing down and going power by power and seeing what multiple of that power fits in our x, right? So we're going to have something like this. We're going to say while that current power is greater or equal to 0, we're going to iterate over that power. So first we got to figure out what multiple of 32 to the current power fits in x. And the way we can do that is by using integer division, right? Because we want to find the multiple of 32 that fits in this, right? So all we got to do is basically just divide x by this, right? So we're going to say x integer divide by 32 to the current power. And we're doing this because we want a whole number, right? We're basically just chopping off the decimals at the end. And let's replace this with the actual Pythonic version of exponentiation. And let's also put some brackets to make sure that Python is interpreting our order of operations correctly. And oops, what's going on here? There we go. And then we can simply add on our result. So this is all we got to do. We have to figure out, right? The current power is going to be whatever spot in the string, or sorry, the multiple is going to be the spot in the string that we want our result to add to. So we're basically going to be adding alphabet at that mult. And hopefully you guys can see that. Maybe I should do an example here just to illustrate what's going on. If we had like 33, right? What's the largest power of 32 that can fit in 33? Largest power is 1, right? So this will be 1, and we'll go into this while loop, and what we want to do is we want to find what multiple of that fits in. Because the next power is 32 squared, right? From 32 to the power 1 to 32 squared, there are a lot of multiples of 32 that can fit in between those numbers. So we need to find out how many, right? How many 32 to the power 1s we need to have in our answer. Because if there's only one 32 to the 1s, well, then we're just using 1, right? And if there is if there's more, then we're going to be using one of these other symbols, right? So that's why we're adding the result thing. So if we find that we need to use, for example, 1, then we're just going to add on the symbol at the right spot, because the multiplier is going to be what we index our alphabet with. So if mult ends up being 1, we are taking 1, which is great. And that's why we have this 0 back here, if you guys were curious, is to account for this mult being an integer division, which means it's going to be 1 onwards. So now, keep in mind that we are recalculating this multiplier every time, which means we need to update x accordingly. So what just happened? We basically looked at the multiple of 32 to the current power that fits in x. So since we already basically took care of that by adding its representative to the result, we should subtract that number from x so that we don't consider it in the next iteration. And so that's very simple. All we got to do is just subtract that same thing that we just calculated. Except this is going to be mult, right? It's going to be mult because that multiplier that we just found times, the current power is exactly what we represented. This alphabet at mult represents this. So we want to start it away from x, and obviously just change our current power, because once we've added this on, we've already taken care of the symbol that's going to represent whatever current power we're on, right? And that's pretty much it. Let's take a look here. Let's try some numbers out, I guess. Here we get 1, 1, which is exactly right, because these are the multipliers. So basically, this is saying 1 times 32 to the 1 plus 1 times 32 to the 0, which is 1, right? This is 1, this is 32. So 32 plus 1 is 33. It's exactly the right thing. We can try a different one, right? Let's put these in prints so that it actually prints it out as a string instead of going to standard output. And let's make our second test case for 100. So you can see this is 3, 4, and this is a string. And this is saying the same thing, right? But it's saying that 100, when we pass it into our function, gives us 3, 4, which is 3 times 32 to the 1, plus 4 times 32 to the 0. And that makes sense, because 3 times 32 is 96. And obviously, we can't fit another power of 90, we can't fit another multiple of 32 to the 1. So the remainder is taken care of in the next power, right? So basically, when we're calculating mults over here, we calculate 3 because, yeah, 100 integer divide 32 is 3. And that's exactly the multiplier that we want for 32 to the 1. So we find that right here, the correct symbol, and we add it on, we just slap it onto our result string using concatenation. We subtract accordingly, and we decrement current power, so that now we're looking at 32 to the zeros, right, for this one. We find the highest power, which is just done like that. It's 4. Integer divide 1, you get 4, and so on. And you multiply, and now current power is below 0, because after this line, it's going to be -1, which means this condition is no longer true, which means we're done the while loop and we return our results. So hopefully that makes sense. Feel free to ask any questions, by the way, about this. Here, we are going to do the same thing, but now we're going to go backwards. So now it's going to take in a base 32 string, and it's going to spit out a decimal number. And so we can have a result, and we're going to return that result. And see, in this case, in the last case, it was a string, which we're returning, because we're going from decimal to base 32 string. Now it's an integer that we're returning, because we're going from base 32 to a decimal integer. And so we're going to need that alphabet, of course. We had a question, can you explain the whole alphabet part? Yeah, for sure. I can try and re-explain the alphabet bit. This one uses it again too, so maybe you might understand it when I do it here, because it's basically the same idea. But if not, I'll go back to the to both these and make sure that you guys understand the alphabet, what's going on here. Basically, using what we just outlined here, you know that 3, 4, this base 32 string is 3 times 32 to the 1 plus 4 times 32 to the 0. And if you had another base 32 string, like for example, let's say 145, this means that you have 1 times 32 to the 3 plus 4 times 32 to, sorry, this would be to the 2, plus 4 times 32 to the 1 plus 5 times 32 to the 0. Right, that's just how bases work. And the same applies to base 10 in decimal, even if you guys don't, like, even if we don't consciously think of it when we do it, that's still how it's working, because all bases work the same, just like that. So what's going on here is we want to get the string in this function, right? Our function is going to take in a string like that, and we want to compute this, right? Which is 1 times 32 squared. What is 32 squared? So we want 1 times 32 squared plus 4 times 32 to the 1, which is just 32, plus 5 times 32 to the 0. So this is what we want our function here to spit out. So how are we going to do that? Well, the way I would do it is you just iterate over and you here. So we can do something like this, right? We can say current power is equal to, well, if this is a string of length 3, that means that the rightmost the rightmost character represents 32 to the 0, 32 to the 1, 32 to the 2. And if we added more stuff, it's still 0, 1, 2, 3, 4. So what you notice is that we always start with 0 on the right and end with the length minus 1 on the left. So if we wanted to iterate over each of these digits and find out what to add to our result, right? Because we're basically going to be doing this, this math iteratively. We're going to first look at the digit that's representing 32 to the 2, find out that it's 1, add this to our result, then move on to the digit that represents 32 to the power of 1, find which digit it is, find that it's 4, and then add that to the result, and so on until we're done, and then we just return result. So current result, we could just say, is equal to the length of the string minus 1, right? And so you could say while current power is greater or equal to 0, once again, what should we do? Well, if we're looking at current power is let me think about this real quick. So if we're looking at, let's go back here, 1, our current power. Okay, so we can make a counter, right? And in this while loop we can obviously increase the counter. But we can say that number that we're calculating, or we can call this like addition or whatever, is equal to whatever this 1 represents times 32 raised to that power. So current power is going to be just like that, current power. And we want to find the multiplier. So the multiplier is just the string at that spot. So it's going to be the string at I times this thing, right? Because this is the multiplier that we're looking for. So when we hit 1, right? Oh, you know what? Okay, actually, sorry. I'm going to do this. I'm going to say while I is less than the length of the string. Yeah, this makes a lot more sense. And then we're also going to, we're going to decrement current power over here. Cool. And so once we figure this out, right, it's just a matter of adding it on to our results. So we could do something like that. Or to save space, we could just like we're just calculating this variable and then adding it on. We could just do results plus equals right here. And then we don't need this sign, right? And let's see, does that make sense? Let's think about it. We define our results. We define an alphabet, which we're going to be using. Oh, we don't actually use the alphabet. Oops, that's probably pretty important. That is very important. So S at I is going to give us a number, right? Or sorry, not a number. It's going to be a digit, which can be a character. It can be a character. So we got to figure out which one that is. S at I could be 1, which means we want to go at 1. So what we're going to do is we're actually going to index it. So it's going to be something like, I believe this is it. I believe index lets you find Yeah, so what I think is going to happen here, right, is if we use index, is it's going to take in a character and it's going to tell you at which index this occurs at. And that's important because the index at which it occurs at is the multiplier that we want, right? Because if instead of 1, this was like j, then that means that instead of multiplying this by 1, we're multiplying it by whatever j represents. So here, or like, let's just use b to make it simpler, right? Here, b represents 11. So b would be 11 here. So what is b? B is the thing at index 11. Index 11 right here. So yeah, so this makes sense to me. And hopefully it makes sense to you guys too, because the multiplier is actually going to be the index, the index at which it occurs in the alphabet. Yeah, cool. So I think that makes sense. We can try returning our result and see if that works. So let's try it out. Let's say print, and we're going to call it. And I believe we had already calculated 145 as 1157. So we'll say down here that 145 should be going to 1157, and let's verify that that's actually correct. I really hope it is. It is. So you can see that when we run this, we print out 1157. We can try it out with other test cases too. So we know we're right because we found this number out by doing it by hand. We actually calculated it using this method. So we know that our function is correct. If we had a, like, let's say like m v, sorry, like, yeah, let's do like ml x 9 4. This is a valid base 32 number because it's using symbols from the alphabet. So what does that represent? Oh no, sorry, we can't use x, of course. Let's just do this, ml94. Yeah, that's already a huge number, right? Because this is base 32. So 32 to the 1, 32 to the 1, 2, 3. So 32 to the 3 is a very big number, and we're multiplying that by whatever m represents over here. So Lacey, I know you said that the alphabet part was a little bit confusing. Do you understand how we're using the alphabet in both of these functions now? Or rather, does everybody understand, or should I try and explain a little bit further how we're using the alphabet and why we need the alphabet? Okay, I don't see anything in the chat, so I'm gonna assume that hopefully it makes sense. Yeah, we are sending a string. Okay, great. So assuming that this makes sense to everybody, or at least relatively enough sense. Oops, sorry, let me zoom back in. That's pretty much it, I believe. So we can go over questions you guys might have about A4 or A5. I know Lacey had one about A4, specifically the bonus question. So we can take that up. And yeah, let's think about it. Okay. So I do have the solution, and I can show you guys what the solution is. I haven't actually taken a very long look at this problem, but we can try and take a look now. I'm going to, it's a bit long. Let's try zooming out a little bit. Hopefully that's still big enough for you guys to see. Yeah. Okay. So what am I going to do? I'm going to copy over the actual question, which is right above here. I'm going to put that in there. So this is what we're looking at. Privacy has been a major talking point amongst many blah, 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 blah. Define a function that takes a message, a shift integer, a lambda function that takes one integer argument and returns an integer. Yep, integer to integer. Cool. So what's going to happen here? So it's going to shift every character. Yep. When shift is a positive value, the shifted character will move in the right. And I'm assuming then when it's, oh, no. It says shift is non-negative. Okay, so it can't even be negative. So shift is just going to be how many shifts to the right you want. So it's saying we have to go through every character C in the string and modify each of them by increasing the ordinal nominal value by shift, creating a new character, C prime. Sure. Here's the catch. This is where the fun begins, I think. The shift for the next character will always change as dictated by the lambda function func. The shift for the next character will always change. Okay, so I'm guessing then this lambda function determines what the shift is going to be for each character. Let's keep reading. The lambda function should receive as an argument the ordinal value of C prime from that recursive call and return you a new shift integer value. And there's a big hint here to use recursion, and it'll make sense why recursion is actually a lot easier to do this. But let's keep reading. In the iterative sense, func supplies you with the next shift value for the next preceding, okay, that's redundant, character, I think. Oops. With a recursive solution, this can be as little as 2 lines of code, first defining a base case for the string of length 1, yep, and then computing the solution in terms of its own smaller subproblems, the remainder of the string. So guys, this is actually something that you guys kind of touched on in test 2 too, this concept here. So what's going on here? We're using something called tail recursion. So what is tail recursion? Tail recursion is a recursive strategy where you look at the first element in a sequence and then make a recursive call on the rest of it. Remainder of that sequence. And the reason it's called tail recursion is because this first element is called the head, and the remainder of the sequence is called the tail. And so you're recurring on that tail. So it's actually really not that bad. This first line here is the base case, as they gave you a hint for, which is how are you going to treat it if you're at your smallest possible subproblem, which is crucial in recursion. You need a base case or else recursion will not work because you'll be recurring infinitely and you'll never be approaching a base case. The whole idea is that every time you recur on that remainder, you're slowly getting closer and closer to the base case with every single recursive call. Here, the base case is determined by having a length of 1. So in order to get closer to a base case, we have to make the length get closer and closer to 1. And the way we're doing that is by decreasing the length by 1 each time here, right? Each time we're only recurring on the string minus that first element, which means the length of that string is going down by 1 every single time. And the rest of it's not too bad. Because obviously, for a length of 1, all we're doing is shifting that message's first character. And so hopefully these like nested things aren't confusing you too much. But basically, we have MSG at 0. We take its ordinal, right? Which means its number as an ASCII value, right? Some hints for this question. Ord takes in a character, returns that char's ASCII value. And I'm sure you guys know from ASCII tables, basically the ASCII values for letters in the alphabet go up one by one. So for A, it's something like 65 or something like that. And it goes all the way up to like 90 something, right? 90 whatever. And there's a different set of ASCII values for the capitals. But basically that means that if we wanted to shift a character by some number, the way we could do that is by simply finding its ASCII value, adding the shift to that ASCII value. So let's say, for example, let's just take a quick look at an ASCII table. And for anybody who wants to stay and watch this solution, feel free. I know tutorial is over. So with that being said, thanks for coming, guys. Hope you learned something. And I'm going to upload the tutorial notebook to Avenue as usual. But yeah, I'll see you guys next week. And for now, I'm just going to keep on going over this question. So let's pull up this image right here. Oh, whoa. That's a bit annoying. Okay, cool. Sorry, guys. Basically, we can see that A, where is A? It's right here. Okay, so the capitals do start at 65, like I said. But you can see here that the lowercase start at 97 and they end at 122. So if we take the ordinal of Z, or let's say of like A, we get the decimal value of that ordinal, which is 97. So if we wanted to shift that by shift it to the right by 4, we would just add 4 to it. So boom, 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 we would get 101. And now, once we have that shifted ASCII value, all we got to do is convert this shifted ASCII value back into its character. And the way we do that is with the character, with the CHR. So that takes in a number, a decimal ASCII value, returns that the corresponding character. And so what's going to happen here is that, well, yeah, I'm sure you guys can see what's going on here. We're basically just doing what I showed you guys over here, right? We find the ASCII value of the first character, we shift it over, we take the character that corresponds with it. Now that's the base case. That is the arguably the easier part of this problem. Obviously, the part that's harder is to find out how to actually make the correct recursive call. And the way we do that is, once again, pretty simple. We do our little tail recursion where we shift over the head, but then we use the fact that the lambda function func is returning the new integer value that you're going to be wanting for the character that you just called, right? So what's going to happen is we take the first one, and in order to shift the rest of it, all we got to do is just recur, where we're calling encrypt again, which is this function, right? With the whole string excluding that first character that we already took care of over here, right? And what we're doing is we're passing into that lambda function, and this is probably the bit that people didn't get, the character, the shifted characters ASCII, right? So what it says here, yeah, see, it says here the ordinal value of C prime. So lambda should receive as an argument the ordinal value of C prime, which is exactly this, right? Because the ordinal value of C is just message 0, and you take the ordinal of that. C prime, all you got to do is just shift it. And so since this is already a number, we have an integer, which is exactly what is specified over here. Lambda takes in that shifted ordinal, which is a number, and returns, it says right here, returns the new shift integer that you're going to be shifting with. So you know that encrypt takes in the message, takes in the shift, and it takes in that function. And so the shift in your recursive call is simply going to be the result of that lambda function with the shifted ordinal for C prime. You're basically just following the instructions for this one. They kind of just tell you what to do, even if you're not 100% sure about what's going on with the actual string. If you just followed this, you would probably fall into the solution. They kind of direct you to it. But if you do want to find out what is happening with a string, you can see that once you understand what's going on with the tail recursion, which is what I specified over here, we're using string concatenation to basically find the encryption of the first character, and then find the encryption of the rest of the string recursively, and then just combine them. And basically what ends up happening is that you just basically use string concatenation to glue the encrypted first character with the encrypted rest of the string, which is just going to recur, and it's going to do the same thing, right? This call is going to break down into this, and then this call again is going to break down into this and this, and so on. Does that make sense to you, Lacey? I know you're the one who asked for this bonus question. I will save this, and I'll also include. Well, actually, we might reuse this. So, like we might reuse this in future classes. So I'm actually not going to include this in the actual notebook that I upload to Avenue. But if you want to take a look, or maybe copy it down real quick, you can go for it. But yeah, if anybody has any other questions, feel free to ask. And if not, thank you again for coming. And yeah, I will see you guys all next week. I'll stick around for a couple minutes to see if anybody asks any questions, and then I'll head out. But yeah, bye guys.